So in this video, or in this problem, we're asked to construct a series for f of x equals e to the 2x. Now, we're not given a center or anything, so, we're not really given a lot of information here. We could center it around 0. That would be a reasonable place to start. And we could start computing derivatives. Unlike regular e to the x, these derivatives won't always just be e to the 2x. It'll have a coefficient that'll keep changing. So we could do that. Or we could recall that, hey, we've already worked out the series for e to the x. So we actually want to use that series. So recall that e to the x was the series as k goes from 0 to infinity of x to the k over k factorial. Right? And recall from before that if we're plugging some expression, some polynomial in to that series, then we can actually just plug it into the series and work it out. And that'll converge as long as the thing inside is inside the interval of convergence for e. But remember, e converges for all real numbers. So as long as 2x is a real number, this series for e to the 2x will converge as well. Okay, so let's check that out. So what this would mean then is that e to the 2x would be equal to the sum of 2x raised to the k power over k factorial. Right? And so that would simplify to be the series two to the k over k factorial x to the k. And that would, of course, be k equals 1 or 0 to infinity. And from our composition rule from earlier, this thing should converge for all real numbers. This thing should converge as long as 2x is inside the interval of convergence for e to the x function. Now, we could go ahead and, if we wanted to, and check this with the ratio test. And what we would find out if you did the ratio test is this would simplify. It would be the limit as k goes to infinity of 2 absolute value of x over k plus 1. But 2 and absolute value of x are just constants as far as k is concerned. So as k goes to infinity, that denominator k plus 1 would go to infinity, and so that would go to 0. And so it would always be, no matter what x is, it would always be less than 1. So we could verify that, but we don't have to because we have that result that from before that told us that if we put a function inside of another function, so that rule 3, right, into a series that converges, then it'll converge as long as h of x converges is in the interval of convergence for the original series. And so that's how we're able to quickly say, not only is e to the 2x equal to that, this is actually going to converge to e to the 2x for all real numbers.